Thank you, Shahar and Abby, for inviting me to have a chance to share with you some of my some of the history of the word invention is not quite correct. The proper word is discovery. And there's a difference between discovery and invention. Just like you don't say Columbus invented America, you say Columbus discovered America, okay? And I said that is because, from yesterday's panel discussion, where some of the panelists were trying to predict which of the various contenders might be the winners, like CBRAM, RRAM, RRAM, all kinds of non-volatile memories, and someone included the memristors as well. And there is, again, a bit of confusion because memristor is not one of those things to be considered as a contention. And the reason is that's the first thing you didn't know about memristor. There are 10 things, okay? The first thing you didn't know is that, I say you didn't know because nobody asked the question or contested. The first thing you didn't know is that all non-volatile solid-state memories are memristors. So therefore, memristor, if you want to really run the memristor, is the winner because any one of them is a memristor. The winner is going to be memristor. Okay? So memristor is not a particular device. It's the whole family. Any device, any non-volatile memory, it has to be non-volatile. Okay? And I can prove to you that it's a memristor. And so that's the first thing you didn't know. The second thing you didn't know is that in contrast, that all non-volatile memories are memristors, but the second thing you didn't know is that not all memristors are non-volatile. That's interesting. So that means that there are the class of memristors, the universe of memristor is much broader than what you might imagine. In fact, there's an even broader class, which in some sense, you will see to the, I believe, more important, which are non-volatile. And together, you will see that this memristor is much more significant than a sort of an unintelligent, dumb memory. In fact, the real importance of memristors is that it is, in fact, what our brains are built from. Our brains are built from memristor, and you see why today. And so if you want to build a brain-like machine, or even an intermediate non-von Neumann machine, you are going to use memristor because otherwise it's artificial. And you have to be able to make it where the ingredients, the building block have got to be certainly in a sub-nanometer range to be able to duplicate the complexity of the brain with the right aspect ratio. Okay, so with this, I would like to begin my I apologize that I didn't have time to put my slide together, so it's going to be a bit more impromptu. And so I'm going to be using, in fact, so please ignore those things on the left just for my own. This is the superset. I'm going to pick up things along the line. And so I'm going to talk about 10 things you didn't know about memristors. Okay, so the first thing is interesting, and a lot of people have been asking me what led me to come up with the concept of memristor. And it turned out that there was what I call a perfect storm in nonlinear circuit theory in the late 50s, in fact, the early 60s, to be precise, 1961, when I went to MIT. And at that time, there were two important events that were discovered. And there were two electricals. One is a device, the other is a circuit. And they discovered both became the Nobel Prize winners. And they both triggered almost at the same period what I call a perfect storm. And now what is that? What do I mean by that? Well, the first one, all of you will know Tanner Dyer, and it's Leo Esaki. He discovered this device. All of these are two-terminal device. And the beauty about this is that it is non-monotonic. And it looks like a very simple device, but nobody really knows how to handle this correctly. And in fact, if you look at the simplest possible circuit, put it just for simply 1 Henry inductor to make things simple, connect it to this device. But you can put any equation. In fact, just pick any equation that has a hum, non-monotonic. The same thing is going to happen. And I picked it because it's so simple. Now you see what's the question, what's the solution given any initial current? Well, if you look, the voltage here is across the inductor, it's the same voltage across the Tanner diode or Esaki diode, but the current is a negative of that. So therefore, the inductor V is 1 dL didt, but this curve is, the voltage is always positive. So it means that for any initial condition in this curve here, the current must always decrease. That's the dynamics. That's clear. Okay, now pick any initial condition, say here, it must decrease. So I don't care how long it takes, but what's important is it's going to be finite. Why is it finite? Because this point is not on this axis, so that it will never be taken infinite time. So it's going to be there in finite time, and at that point on, you say, what next? Well, you can't go back up because the law here says the current must decrease. So it can't go back up. And that's the paradox and enigma, and I call that an impasse point years later. I remember asking my professors, the top professor in the whole MIT, including the father of circuit theory, Gilman, and nobody knows how to handle this. And if I would invite you to just put this in a computer, by the way, use any software you have, any Spice or anything, and ask for the answer. Where you see that either your computer will just stop some, or it will just give you a nonsense answer, because the correct answer is mathematically, the correct answer is right there. No more solution after that finite time. In fact, for a mathematician, no solution is a perfectly valid solution. Perfectly valid. That is, in fact, the correct solution. But for everybody else, no solution means nonsense. Okay? And so that's the first storm. How do you resolve this problem? And the problem is that pre-1970, I say pre because my paper was published in 1971, it turns out that the 3 basic circuit elements actually give wrong answers if the circuit elements are nonlinear, such as the Esaki diode, and connected in an appropriate situation, or time varying. And time varying is important because this is the second storm. I just mentioned there were 2 storms. The first storm is this impasse thing that nobody knows how to answer. And the second thing is what happens when things are time varying. Now, all of you have brought up, including myself, that these are the 3 classic elements. With von Kleist, the first capacitor is 1745. I is CdVdt. Ohms comes along, and that's what we call Ohm's law. And then farther that comes last, we have the inductor, okay? And it turned out that if you make the capacitor time varying, and you see that, or any one of these, you see that you are going to get wrong answers if you just plug in this formula. So there's something wrong with this formula, and the reason is this formula were so ad hoc introduction. There were no formal solution, foundation. So to recover from the perfect storms, capacitor inductor has to be redefined via what I call an axiomatic approach. So the reason for the axiomatic approach is that it does not depend on anything, the material, the structure, how it's made for. Strictly, you have a block, but you have 2 walls coming up. You allow only to perturb from the outside, make all kinds of measurements. Whatever you determine is therefore independent of the material. That's why I say it's timeless. Okay, this is the axiom. The axiom for definite circuit element is that there is such a thing. In axiom, you have to have some undefined concept. The two undefined concepts is there is such a thing called a voltmeter, and there's such a thing called an ammeter. Okay? And so whatever you measure across with it, you call that a voltage, and I use the symbol V for the same reason we used V before. And whatever you measure from a current, ammeter is called current, and I use the symbol I. These are the undefined concepts, okay? Voltage and current. So you don't even need to know about electrons or electric field, nothing. Just you have a voltmeter, ammeter, you go to some store, you buy them, you make measurement. And let's imagine that you can keep all those in your computer. So given, if you measure any voltage waveform or current waveform, you can, I'm sorry. Okay, so the fact that you can measure current waveform, you can certainly integrate it, and I call the integral Q. It just so happens because that Q is a charge, but the axiomatic definition does not require you to know anything about charge. I just use the same symbol, okay? Which means that anything that you integrate is this variable. And since you can measure voltage, you can integrate the voltage, and whatever you integrate, I call it flux, just for the reason we already have a name for that. But it doesn't have to have a physical meaning of flux. So you can see this is the axiom, okay? And now, you give me a device, how do you know it's a resistor? Well, how do you know it's an inductor or capacitor? Well, the way to define this is that you imagine a Gedanken circuit. You can have as simple as a voltage source, or current source of any waveform, or you can put anything, any circuit with some voltage source and current source, any number of them. Just imagine it's a Gedanken, okay? And whenever therefore you can measure the current and the voltage. So you have a pair of waveform for one measurement. And imagine you did it for all possible Gedanken circuits. And if you imagine you have infinite memory, that read-up table, in fact, is the correct model of that. But of course, that's a Gedanken. It's completely impractical. But what if that for a certain device, you were able to find that all the voltage current pairs that you measure happens to all fall on a curve, a well-defined single-valued curve. I say for all, not just for one or two, but for all. Well, if that's the case, I call that a resistor. And that curve may have been a straight line. Every straight line is just Ohm's law. So we recovered the correct, the formula we all learned. But what if the device didn't obey that, but it happened to obey a relationship between current and flux? Well, in that case, that device is going to be called an inductor. And when it's linear, then phi is Li. And if you differentiate twice, it's V is LD, IDT, that's inductance, okay? And what if it is neither of two, but it may obey a relationship between charge and voltage? And in the linear case, that would be the usual formula. So I recover the standard formula we all learned from high school. And when it's nonlinear, it gives you the right answer, okay? There's no more anomaly. Now, so if you assume that this axiomatic approach is if you believe in it, then it's obvious, completely obvious that there's something missing. And so for completeness, I define a new element because that was the missing link. And that was my 1971 paper. And I call this Memristor, which is the shorthand for memory resistor, because that element has a very simple property, namely it obeys Ohm's law. So that element, it obeys Ohm's law. The only difference is that the resistance is not constant. In this ideal case, that resistance depends on the charge. So we can say that ideal memristor is a charge control Ohm's law. Or you can use flux as an independent variable which means you drive with the voltage, and you can say it's a flux control Ohm's law. Those were the ideal memristors. Okay, so just to give you a quick example, pick any charge control memristor. So this is a flux. Assume that this is any nonlinear curve. So if you have a device that obeys a particular curve, single value curve, phi is f of q, then that's a memristor. It's an ideal memristor. It's a current control memristor because the integral current is the independent variable. Now, if you differentiate both sides by chain law V is d phi, the f dq, dq dt, and that, of course, will be another function of q, and that's m of q, just which is the slope. And I is happen to be the q dt by my axiomatic definition. So this is the equivalent, complete equivalent definition of an ideal memristor. Or in the dual case, it'll be I is equal to, this is the memristor, memory resistance, the converse will be a conductance. Okay, either way, it's the obvious dual of each other. Okay. In fact, I have since found that all of the non-volatile memory that have been reported in the literature, all can be described by this formula in a more general sense, and I will quickly go there shortly. So, in fact, before I do that, let me just say that memristor for all practical purposes can be defined as simply as a state-dependent Ohm's law, except that the Ohm, the resistance, is not a constant. It can depend on one or more state variables. And by state variable means it obeys a differential equation. So that's what it is. Any of the memristor, non-volatile memory, all going to have this property. They are state-dependent Ohm's law, okay? And it turns out that in my paper, as a proof of concept, I actually designed and built a circuit using op-amps and transistors. And indeed, it works exactly what it should be, relationship between charge and flux. So I did, but it's completely impractical. First of all, I need batteries, and it's totally useless. And I didn't realize, though, that in 1973, when Josephson, after he got the Nobel Prize for his famous invention, and this is a circuit, by the way. Interestingly, several of these Nobel Prize winners actually got the Nobel Prize for a circuit. So it's Josephson, and in fact, the Josephson circuit that Bell Lab built consists of these first three elements. That is in the original Josephson paper, and it has a capacitor and a resistor, and an element that Josephson didn't know what it is, but he had a formula. Current is a constant times sine of phi. And now, of course, today you know that something that relates current flux is an inductor. So that is an inductor, but it doesn't matter. He had the right formula, and that's enough to give him the Nobel Prize. After he got the Nobel Prize, he went back to his quantum mechanical days and tried to be more precise and realized and published another paper for posterior reason to say that, well, I'm not quite right. He missed a small component that is negligible. The fact that it was built by Bell Lab and worked is a lucky thing because this happened to be very small. But Joseph would say you need another component. And he didn't know what it was, but he said this is from a quasi-particle current interference. But he published a paper, Josephson, and said that, look, there's another component, very small, but it has a formula, it's an Ohm's law again, but it depends on flux. Well, today we know that, just now, we know now that that is a memristor, okay? So what I'm saying is that when I published my paper in 1971, in fact, if I had known about this result, of course, it wasn't done until Joseph got his Nobel Prize. All these four elements are already included in the original fourth basic circuit element. Okay, now, why is this non-volatile? Well, if you take a memristor, pick a curve like that, Q5, pick a arbitrary square pulse. So if this were a resistor, if you put a plug again, everything goes to zero. No memory, right? But remember, this is flux, is independent. So even though you go back to zero, the flux stays constant. So they say that it starts to integrate and there, After you pull the plug, that point remains there, and the resistance remains there. That's where the non-volatile memory comes from, okay? That's all non-volatile memory, essentially based on the same principle, okay? Now, it may so happen that this could happen to be just two piecewise linear segments with a corner there, and the slope here is 10, and the other one is 0.1, and so you can say that that particular memristor is binary, has a 10 ohm and 0.1 ohm double state. Those were the two binary states. Okay, so I'm going to quickly go on since I got to give you more example. The next thing that you didn't know is that what happened if you connect a battery directly across, well, I'm talking about, I mean, maybe 0.1, 0.3 volt, like what was mentioned yesterday as the minimum that you would need. I guess Eli was saying that, well, whatever, no matter how small, even 0.05 volt DC, no matter how small you connect there, what would happen? Well, it turns out that no matter how small you put in, for most memristors, such as this one, where the slope increases to infinity, what are you going to see? Smoke. And the reason is very simple. You have smoke because when you put in the battery, a DC, you integrate that, you got initial flux plus E times time, and no matter how small E is, as long as it's not zero, it's going to integrate, and so this is going to go, and sooner or later it's going to blow up. The shocking truth, therefore, is that memristor has no DC VI curve. Most people didn't realize it. In fact, it's completely reasonable. You can ask yourself, you have read hundreds of papers about non-volatile memory. Why is it nobody ever gave you a DC VI curve? Well, the author didn't know either, and the reason is it doesn't exist. They tried, and I'm sure they're embarrassed that they burned out so many of them, okay? The reason is it doesn't have a DC VI. The only DC VI curve that a ideal memory had is the origin itself is a 1-point VI curve. So that's the thing that you didn't know, I'm sure, okay? So the ideal memristor does not have a DC VI curve, okay? But of course, in real life, this is not true, but everything I talked today is ideal, which means the state, so this is the state equation for the state. Remember, memristor, as I define it, is defined by a state-dependent Ohm's law, and you have a state equation. And the most general state equation is of this form, but I'm assuming that the state variable is infinite, right? Just for simplicity. There's no loss of generality. You can easily put boundary conditions to look at the specific cases. So in the real world, you either burn up in some time, or it exceeded the boundary, and you no longer have a memristor. So that's no longer within my talk today. So there have been many memristors that have been the latest, in fact, are just 2 nanometers. This was 2 years ago by Professor Chua, and this is a 2-dimensional. Yesterday, they were talking about this molybdenum disulfide, and this is like a graphene thing, and you have this memristor. Now, it turns out that all of these memristors that has ever been reported, first of all, it doesn't have a DC VI curve. So what's the next best thing you can do? Well, the next best thing you do, you put it as a periodic input. Make it sufficiently low frequency, and you hope that whatever you trace, you can call it a DC VI curve. Well, we now know that is not quite correct, but at least this is what you see. And you will see that there's a fingerprint in all of them, and that is, it's a hysteresis curve, but what's important is always go through the origin. It can do different crazy things, can intersect, and every time you change the waveform, the frequency, amplitude, you're going to get a different curve, but what's important to make sure the memristor is that it's got to go through the origin. That is the signature, and so this is why the correct way, the best way, because out of these hundreds of papers published about non-volatile memory, I can count less than the number of fingers in my hand that has equation. because it is so hard to derive some equation. So how do you know you're working with a memristor? You don't have equation if you want to be strict about it. So the best way is what I call the experimental definition. And that definition is very simple. If it's pinch, it's a memristor. If it's pinch means though for all possible periodic input. But in practice, of course, if you test it with, say, a few of them, and you'll find you always go through origin, I can almost guarantee you have a memristor, okay? And conversely, by the way, that's another thing you didn't know, and my friend Devendra here also didn't know that it's opposite is also true. If it's not pinch, it's not a memristor, okay? And I proved for that if we have time, okay? So if it's pinch, it's a memristor. If it's not pinch, it's not a memristor, okay? All right, now, so this is the genealogy of memristors. You can see that from the ideal memristor, which is this one, and you can make an obvious one-to-one transformation phi. Say phi is equal to x cubed. And you will get, of course, a different equation. So you can say, aha, this is not ideal anymore. But in fact, it's exactly the same thing. The VI curve, the principle will be exactly the same. So these two are really the same. This is the sibling of that. So I call this an ideal generic memristor, because generic means the same formula, except that this thing is a bit more general. It's not just multiplied by V, but V inside. And finally, the most general case is that you would allow, it's the same state equation, but you generalize by allowing the memristor, the Ohm's law. All of this Ohm's law depends only on the state. But you can allow, in the most general case, Ohm's law that depends not only on the state, but also on the input voltage, under the assumption that this doesn't blow up when the voltage is zero. And this was the mistake that Devendra made, and I call that his mem capacitor erroneous for that reason, because I have proof that it is erroneous, okay? So this is the universe of all memristors, okay? So that's the first part of my talk, and I already consumed half of my time. So I'm going to have to rush a bit. All right. Let me. Oh, I guess I ought to address now, make a strong statement. That's another thing you didn't know. And that statement is say all non-volatile memristors based on resistance switching. Important here is I'm not claiming anything. I'm not talking magnetical as memory. I'm saying that as soon as you use the word resistance as your memory, you have a memristor. Why? Because what is a resistance? Resistance is defined only with Ohm's law. Otherwise, how do you define resistance? And as soon as you use resistance, you automatically, your device is a memristor. So memristor is a concept. It's not an invention, okay? All right. Now, by virtue of this, you can clearly say that all the RRAMs, all the non-volatile memory, and this is a subset, RRAM, phase change memory, MRAMs, CBRAMs, ferroelectric non-memory, magnetic tunnel junctions, atomic switch, and you name it. As long as you use resistance as your binary thing, you have a memristor, okay? And there are all kinds of ways to make memristor. You can have polymeric, you can ferroelectric, you have manganate, spintronic, whatever. In fact, there are people who just published that last year, even egg white. Just use egg white, you can make memristor. There are all kinds of ways, and they're all memristor. Why? Because it has a pinch hysteresis loop in the VI plane. And if it's a pinch hysteresis loop in the QV plane, you have a mem capacitor. So mem capacitor, mem inductor, these are all trivial. You just change the word, you have all the others, okay? All right. Now, for historical reason, it turned out that, again, you didn't know that, the first radio, we'll talk about first radio, actually it's not as complicated as the box you saw, it's just this contraption. This is just a galena crystal. And in fact, I actually built that when I was a kid, okay? And I never realized that someday somebody would measure that, and it's a pinch loop. If it's pinched, it's a memristor. So you can say that the galena is, in fact, this whisker radio is a memristor as well, okay? Okay, that's Xpoint. In fact, for interesting thing is that most of the people who publish papers don't show the whole pinch loop, you know, and they like to show the log of that. First of all, it saves space, so you flip it over, and also it gives you a bit more accurate on the logarithmic scale, so you can say how much, what's the ratio of your high and low resistance, okay? But the interesting thing is that they are, of course, exactly the same, and the shape, but it's always this one. It was amusing to think that this is exactly what I call a golf wing. And like the Mercedes, that is the standard fingerprint of a non-volatile memory. And now you have Xpoint. You can see you got this multi-level golf wing. And but it turned out that the quest for building nanoscale solid-state non-volatile memory dates back to 1939. Interesting, okay? Solid-state. And this is, in fact, that I just copied that, you know, published. And this is not a film, but it's solid-state. It's boron, okay? And Bruce the Hickling had the insight of build after he measured. This is the first pinch hysteresis loop that I've ever seen that I can trace back, okay? And then, but they don't know really what this device is. And the closest one that most people recognize today as the first memristor is Xpoint. And this is widely referenced. Again, he's got pinch hysteresis loop. He didn't realize the significance. In fact, he was most of this paper overwhelmed with negative resistance. So they were looking at the wrong horse. Okay? What they should realize is that this pinch thing is what's important. Okay? But I want to mention something from this paper, because not only did Xpoint realize that this is a memory, a non-volatile memory, he also said if you take small signal conductance at 0 DC bias, so if you want this to be non-volatile useful, you don't want to have any bias, right? At DC, and if you can, that he can continuously vary the conductance by applying voltage pulses. So he's the first one that I've seen that recognized that you can tune the resistance by applying pulses. Moreover, he found that if you increase the pulse amplitude, you can decrease the pulse width. You can trade off the thing. That was an observation that I copied from them, and he didn't realize the significance. In fact, many papers these are all papers in 60s, 63, they all pinch hysteresis loop. But I want to go quick. By the way, there's an interesting Japanese paper published in 1971, same year that I published my paper. If I knew it, I would have referenced that. He was the first person to recognize there's something interesting about the hysteresis loop. It's not just any hysteresis loop. It's got something that's in the title, letter 8. And so this is the first person to recognize the significance of the fingerprint is this pinch thing, okay? Because most people are brought up with this square law magnetic thing, okay? Now, so less than 10 papers, in fact, been published between 1970 and 2000. There was just absolutely almost nothing, okay? So I said there were 55 years of confused and misunderstood non-volatile memory devices until this paper, 2000. And this is, again, it's a pinch hysteresis loop. So we know now it's a memristor, but they didn't know that that's really enough to know that there's a non-volatile memory. Then what's interesting, though, is that the paper repeated what was observed by Hickling 55 years earlier. And that is, a negative pulse of 2 milliseconds will switch the system into the low impedance state. And after applying a positive voltage, positive pulse of 2 milliseconds, information region is erased, and you get high. So he's saying that you can switch back from high to low resistance with a pulse, exactly what Hickling had observed. They also observed that faster switching speed. That means that the shorter, right, pulses are used. It's also possible, but require higher voltage amplitude. And many more papers have been published, all realize that you can use pulses and that you can control the width, you trade off the width with amplitude, okay? And nobody knows why, but I said this paper had been since been the standard reference, not only because it is more carefully documented, but because the second author happens to be Berkeley, that all of you know, and I believe that was the reason why this has attracted great increased interest ever since that published paper. But all of them are using now pulses. Because first of all, why don't you use battery? Because it burns out, right? So you use pulses, and they all have the same phenomena, and I have proved. I now have a theorem which proves that it obeys this hyperbola or exponential law. So you can make it faster, but you have to increase the amplitude. So this is actually a law, I mean a theorem that I had proved. Okay? Now, since then, there are tons of pins in series loop, and if it's pins, it's a memristor. They're all memristors, okay? So, but not all memristors are non-volatile. That's what the next part of my talk, and that is interesting, I believe. So I'm going to very quickly start with this. This is the picture that Dr. Kandel shown when in year 2000 when he was receiving a Nobel Prize and he had to give a lecture. And the first slide he's shown is this picture. So this copy from his book. And this is the Nobel Prize medal. And Kandel said, I dedicate my talk to this little chap. It's called aplysia. It's just a snail, sea snail. But this is the animal that allows him, because it has very big neurons. This was work done in the 50s. And you can actually see your eyes. You can poke this electrode at all kinds of places. And it was through this that he got his Nobel Prize, because he discovered the molecular basis of memory. So all of this has to do with memory. And so the way this works is that this animal has a tube that for breathing. So it's very delicate. As soon as this animal sense some danger, it would immediately withdraw. So you need to have some signal to contract the muscle, okay? And so what Kandel did is put in an electrode, a sensor there, and a sensor that, and then he touched it gently, and you expect to have a signal, an action potential, and then that will propagate to go to the muscle to contract, okay? So he made 15 experiments, Kandel. This is in his book again. I copied it. So the stimulus are 15, and he showed only 5, so I copied the 5. And they're all action potential. They're all identical. As you expect, every action potential should be identical. But what Kandel observed is that after the first big pulse in the muscle contraction signal, it was a huge one, so it was quick contraction. But then the second one began a little smaller, and in fact, after a while, it's almost no contraction. So this is the most elementary form of learning. The chap, the priest has learned that it's not so dangerous after all, because it consumes so much energy to contract not much. So this is learning, okay? And that led Kandel to the molecular basis of that, to his Nobel Prize. Now I want to show you that I have a simple Ideal Memristor with a curve like that. And remember, the slope are the conductances. And if I just drive them with identical 15 pulses, make it simple, then if the conductance keeps decreasing, the current is always decreasing. It's exactly the situation. So I've just shown you that the memristor, in fact, are synapses. Okay? So this, the memristor is, it just can learn, and as it learns, it moves around this curve to give you the different synapses, which translate into the number of neurotransmitters it would emit. So synaptic strength, in fact, is nothing but memriscence. So that's one important result that most of you know, is that synapses are, in fact, memristors. Okay? Now, the second example I wanted to tell you is the second storm that I mentioned earlier. And this is a famous Nobel Prize in 1961. Again, it's a circuit. It's interesting. This is a circuit that for more than 50 years, no one was able to reproduce an action potential until this circuit was invented by Huskin and Huxley. And this remained to be the most well-known circuit available. But what's interesting, where is the storm? Haskins say, okay, this circuit consists of capacitor, 3 batteries, and a resistor. But then he said that there is a resistor that is not constant. For the potassium, it varies with time, and there's a resistor that models the sodium, and it's not constant either. And but they were able to produce the differential equation that you can solve to prescribe what is the time variation. And so that's why naturally they call it time-varying conductance and time-varying potassium conductance and time-varying sodium conductance. Now, the problem is that people started to make measurements, including themselves, and they found that from small signal measurement that they had a very large reactance over certain frequency range, and they were shocked because they were measuring something like 1 Henry, that kind of a thing, okay? And no one can explain why. They published, they call it anomaly. In fact, the famous physiologist, their colleague, Kenneth Cole, that many people thought ought to share the Nobel Prize because he did the main result that led Haskins to make the measurement. Anyway, Kenneth Cole, to show you how serious it is, he said the suggestion of an inductive reactance anywhere in this brain, the system, was shocking to the point of being unbelievable. I'm just quoting this statement. So this is a storm because nobody understands how could you have things like a few Henry in your brain, okay? And no one can understand why. And that's 1 Henry, by the way. So obviously it's shocking, okay? And so the solution is now very simple. Haskins had struggled in vain searching for a physical interpretation of the squid axon inductance. He failed because he had mistaken the axon for the time-varying conductance, when in fact it has a simple explanation when the potassium-sodium ion channels are memristors. In fact, all ion channels I've just shown are memristors, okay? And once you realize that, then the mystery disappears, okay? So this is the correct Haskins-Huxley model. This is not to take away anything from them. It's still their model. It's just that all you need to is to translate this into the equation of a memristor for the sodium and a memristor for the potassium. Everything remains the same. It's classic. Remains a classic. Still the most widely used model. But we now resolve the second storm that they are in fact memristors. Okay? Axons therefore are made of memristor, and synapses are made of memristor. So those are the stuff where our brains are made insofar as intelligence or communication is concerned. So we can say that obviously the brains are made of memristor. Now I'm running quick, but I want to show you yet another example. This is another Nobel Prize in 1904. And the famous experiment is that Pavlov was trying to find out how the dog would react to different kind of stimuli. So most of you probably have seen this before, but let me repeat here. So when Pavlov brings a stimulus sound, the dog was indifferent. It was obviously not very interesting on musical or chime, whatever. But when Pavlov shows a piece of steak, the dog salivates. And there's a good reason for that, because the saliva contains the enzyme needed to digest the meat. But most other people would just say this is not so interesting. But Pavlov had a good sense of this experiment. Pavlov would first show the dog the steak, so he began to salivate, and almost immediately ring the bell. He did it maybe a few times, and then come back maybe an hour later. And then Pavlov would repeat the experiment, except that he would only ring the bell, no meat, but the dog salivates. So that's the first proof of associative memory. The dog is able to associate the bell, the sound of the bell, with the meat, okay? Now, I have a circuit that I want to show you. This was a circuit built in Wuhan, published 15. And this is a real memristor. This is a phase change memory. And put this in a voltage divider. So the first voltage source would be the bell, the sound. The second one would be the mid. And then the output would be here. So we have this experiment. By the way, this, you see my name there, but I've done nothing other than just to confirm to them that if this pinch is a memristor, but they were not sure it's a memristor, okay? And I have absolutely no contribution on this paper. But the interesting thing is that, okay, here is the measurement. This is a real, so we have a real measurement here. First, we get the signal, 3 pulses, and there was a response, but this is foot. And then followed by 3 pulses for the sound with no foot, so there was nothing, okay? And finally, you get a pulse for the foot and of the sound, a pulse and a pulse for the foot, and this is what you measure. So this is the experiment. Finally, no bell, no sound, there's no foot, so no pulses, but only the bell sound, and yet you can see there are signals generated. So this is a demonstration that the memristor is really the stuff that our brains are made for. You only, in fact, need one to emulate the Pavlov classic experiment. The last example I want to show you is another interesting paper published by one of my colleagues from Berkeley, Wu. And again, I have no contribution at all, except that they put my name because they had consulted me and found out that what they had, in fact, is a memristor. And in fact, this paper was well recognized. In 2014, Professor Chua Wu was actually awarded for a Young Scientist award for this particular work. So what is this work? This is a vanadium dioxide, and they didn't know, by the way, about that it's pencil, but they found out that it has interesting property. If you put in, say, a 3-volt DC battery, this is like 2 coils, but you can see that there's a joint here, and when you put in 3 volt, suddenly this thing will spring up. So it's an actuator, okay? It's an actuator. And the reason they did this, but they were trying to devise nano actuator for master, to emulate master. And before they published their paper, they were just curious that maybe this is the memristor. So they asked me, do you think this is the memristor? And I said, well, measure the VI curve, and if it's pinched, it's a memristor. Well, it's pinched. And I got my name in the paper just for that reason, okay? All right, now this is the real experiment. I actually have a video, but I don't have time to show you. There's a little tiny object there, and this is after you put in a 3-volt battery, and then this thing gets spring up, okay? Now, it turned out that this is a very powerful invention. It's 1,000 times more powerful than human master. You can catapult object like that one, 50 times heavier than this, sir. You can catapult object over a distance 5 times its length. It's faster than a blink of an eye. In fact, the author went on to make a comparison. They scale up the device to the size of a 777. And it's well known that 777 is a powerful turbine. It's a power density of 90 kilowatt per kilogram and a rotation per 10,000 RPM. But if they scale up that nano micro device into the size of a 747, it turns out that they have a power density that's 4 times more stronger than the turbine, and it's 20 times faster, 200,000 RPM. So there's something about a memristor, and it's not just memory as well. And I don't understand. There must be something there that has this potential. Now, the next thing that you didn't know is that some memristor circuits have Hamiltonians. Now, remember, memristor Ohm's law. It doesn't store energy. It just dissipates energy. Yet, to make a long story short, I put in an Ideal Memristor, with this simple equation. I put in a 1 Henry inductor to make it simple. It turns, and this would, if you write the equation, this is the differential equation. Well, it turns out that by just a simple change of variable, the I dt, I call it d tau, with that, this equation converts to that, and it turned out that that would allow me to, to define a scalar function, which I call Hamiltonian. This is the scalar function. In fact, I even call this a pseudo-potential energy, a pseudo-kinetic energy. The reason is, with this, I can write the Hamiltonian equation, and it will give you exactly that equation, namely this equation. So I have actually a dissipative circuit that has a Hamiltonian, unheard of, okay? Most physicists would be jumping up and down, how can that possible? Well, it is possible. And this is not a singular point. There are many circuits that would have this property. In fact, we simply calculate, integrate the differential equation. This is the state variable x of t. This is the current. This is the voltage. You can multiply the current and voltage to get the power. And this is the energy. And continue that. You can calculate what I call the pseudo-kinetic potential energy and the pseudo-kinetic energy. And interestingly, adding these two, you got a constant. Prove that it's Hamiltonian. Okay? So my time is quickly running out. So I'm going to rush over. Well, I'm going to, there are many interesting things that I don't have time to talk about. Well, maybe I should at least show this. In 1980, I actually published a paper, and this is a very poor diagram, but this is the diagram in what I call alpha beta, and for every, this is a schematic diagram. This is alpha, this is beta, and if I enlarge that, so alpha means that for any integer here, it is decoded as the alpha derivative if alpha is positive, and alpha integral if it's negative. And beta similarly defined. Well, with this sort of schematic diagram, it turns out that you can identify that the resistor, the inductor, the capacitor from the old days right there, and then the memristor would just fall apart here. And if you continue this diagram, because mine is much longer, you will get the mem inductor and the mem capacitor. So these are not new at all. These just fall along here. In fact, go back to this. By the way, I have a theorem which shows that given any one of those dots, which is a circuit element, you can produce exactly the same pitch hysteresis loop by going one step downward or one step upward, okay? And now what's interesting, though, is that out of this strip here, like I said, the resistor is there at that dot, the memristor is at that, and the mem inductor there, and the mem capacitor there. In fact, you can ask, what else can be built? Well, of course, you can only build this if it's positive. And I have a theorem published in the 80s, which shows that here is, I call it the golden strip, like the golden bit you have in Haifa here. In a sense, along this strip bit, all the elements along this are passive, which means that you can actually build them. At least there's nothing against the law of physics. This remains to be discovered for those who are interested. So far, we got mem capacitor, mem inductor. There be any one of them along below that on this golden strip, they are potentially exist. And then you can ask, what property do they give you? No one yet knows, because no one has studied that. Okay, now I'm going to finish my talk with a true story. Okay, this is, I'm going to first of all demonstrate, first of all, I'm going to introduce you. Oh. Sorry. Okay, I'm going to introduce you to Sir Humphrey Davy, who is a chemist. And of course, you see Napoleon on the left for the reason I will show you in a few minutes. But this is an experiment that Professor Ron Hui from Hong Kong University reproduced an experiment made by Sir Humphrey Davy. And that was the experiment that I suggested Ron Hui to reproduce. This is the reproduction of Davy's experiment. It consisted of 2 carbon electrodes with a high voltage applied between them. And the idea here, this was in the turn of the 18th century, where London is a very progressive society, and where people were clamoring to replace someone to invent an electric light bulb instead of gas lamp. So that was the motivation. And so Humphrey Davy came up with this beautiful idea that if you take 2 electrodes close enough and put a high enough voltage, the spark, if you can maintain it, would give you the light he wanted. And he did that with the help of voltage. That was 1800, okay? And sure enough, I'm going to reproduce this phenomenon, this experiment right now. Listen, let me see. Here is the live experiment now. And remember, this is going to be the first memristor, real memristor. That's why of historical importance. Okay. Listen carefully when the spark thing, you hear the sound. This is one of the postdoc of Professor Ron Hui at the University of Hong Kong. This is spark. Now, hear that? Okay, now how do we know that is a memristor? Well, I asked Ron Hui to measure the VI curve. I say if it spins, it's a memristor. This is its pinch. So this shows that it is, in fact, the world's first memristor. But it is it's a volatile memristor, okay? Now I want to end my talk with a true story. Napoleon, why is Napoleon in this picture? Well, in 1809, you may not realize Napoleon, aside from being a great general, is a fan of science. So when he learned about Davy's work and this spark thing, in 1808, when France was at war in England, you know, the harbor of Hong Kong is all blockaded. Bonaparte still said that he's got to receive this pre-Napoleon, which is more prestigious than a Nobel Prize. And so Napoleon picked one of his embassy people from in the good days who know London well, and asked him, and give him a special letter of invitation, a visa in some sense, to come to London. And this person had know his way how to go to London, and he gave him a whole bunch of gold like this. Okay, take this because the franc would be useless, so it's all gold coin. And so that's what he did. Went to London, found Davy, and said, "Here is the gold." And he also told this man to say, "Bring enough gold and tell Sir Davies to invite his wife as well. If you sell your wife, it's a lady. Lady Jane should be invited." Okay, this is a major event, war or no war. And then Napoleon was so thoughtful. He said, "Look, we got to make this trip comfortable, even though all this blockade. We got to have a servant. Find a servant. Here's more gold coin. Here's a servant. Bring that and hire a servant and have the Sir Davy, Humphrey Davy, and Lady Jane, and someone to carry the luggage, come to Paris, claim the prize." This all happened, and they all come back. So that's the interesting story by itself. But the real reason why this is interesting is, who do you think that servant is? Anybody know who that servant was? Somebody you knew. Well, That's Faraday. He was just an assistant of Sir Humphrey Davy. So this closed my talk because it now closed the circle. We have the fourth basic element from von Kleist, and historically, this is actually predate Ohms, and predate, of course, Faraday. Well, thank you for your attention.